When dealing with a 400 amp service that has a double meter configuration, proper grounding is crucial for safety and compliance with electrical codes. The situation involves two main disconnects, one for each unit, and the question concerns how to properly ground the system from the main disconnect to the panel inside the house. The grounding electrode system should be established in accordance with Section 250.58 of the National Electrical Code, or NEC. This section mandates that all grounding electrodes must be bonded together to create a comprehensive grounding network. Since a grounding electrode conductor is run from the first means of disconnect to the panel, the neutral bus in the panel needs to be connected to that same grounding electrode. This connection ensures that the entire system is referenced to ground potential, providing a low impedance path for fault currents. It is not permissible to use the cold water pipe as an equipment grounding conductor. However, it can be used as a grounding electrode as part of the overall grounding electrode system. The key distinction here is that the cold water pipe, when used as a grounding electrode, must be supplemented by another type of electrode, such as a ground rod or a concrete encased electrode. According to Section 250.24 A2 of the NEC, if you establish a grounding electrode system, the main grounding electrode shall be as close to the service entrance as practicable. This proximity minimizes impedance and ensures effective grounding. Here is a breakdown of the steps and considerations for grounding this type of service. Firstly, establish the grounding electrode system. This typically involves one or more grounding electrodes, such as ground rods, ground plates, or concrete encased electrodes, often referred to as U for grounds. The choice of grounding electrode depends on local soil conditions and code requirements. Secondly, bond all grounding electrodes together. This means connecting all the grounding electrodes to each other using a grounding electrode conductor. This conductor must be sized appropriately based on the size of the service entrance conductors, in accordance with NEC Table 250.66. Thirdly, run a grounding electrode conductor from the first means of disconnect to the grounding electrode system. This conductor connects the neutral bus in the first disconnect to the grounding electrodes. Again, the size of this conductor must comply with NEC Table 250.66. Fourthly, connect the neutral bus in each panel to the grounding electrode system. This can be achieved by running a grounding electrode conductor from the neutral bus in each panel back to the main grounding electrode system. Alternatively, a single, larger grounding electrode conductor can be run from the first means of disconnect to a common point, and then separate conductors can be run from that point to each panel. Fifthly, ensure proper bonding of metallic water pipes. Although the cold water pipe cannot be used as the sole equipment grounding conductor, it can be used as a grounding electrode if it is supplemented by another electrode. If the cold water pipe is used as a grounding electrode, it must be bonded to the grounding electrode system with a bonding jumper sized according to NEC Table 250.66. Additionally, any interior metallic water piping that is likely to become energized must be bonded to the grounding electrode system. Sixthly, do not use the neutral conductor as an equipment grounding conductor. The neutral conductor is intended to carry unbalanced load current and should not be used to ground non-current carrying metal parts of equipment. Instead, a separate equipment grounding conductor should be run with circuit conductors to provide a low impedance path for fault currents. Seventhly, inspect and test the grounding system. After installation, the grounding system should be inspected to ensure that all connections are tight and that all components are properly installed. Additionally, it is advisable to test the grounding system to verify that it is providing a low impedance path to ground. This can be done using a ground resistance tester. To reiterate some key points, firstly, all grounding electrodes must be bonded together to form a comprehensive grounding system. Secondly, the cold water pipe can be used as a grounding electrode, but it must be supplemented by another type of electrode. Thirdly, the neutral conductor should not be used as an equipment grounding conductor. Fourthly, the grounding electrode conductor must be sized appropriately based on the size of the service entrance conductors. Fifthly, the grounding system should be inspected and tested after installation to ensure that it is functioning properly. Some additional considerations include the following. Firstly, the location of the grounding electrode system should be as close as practicable to the service entrance. This minimizes impedance and ensures effective grounding. Secondly, the grounding electrode system should be protected from physical damage. Ground rods should be driven deep enough into the ground to prevent them from being bent or broken. Ground plates should be buried at a sufficient depth to protect them from damage. Thirdly, the grounding electrode system should be accessible for inspection and maintenance. Ground rods and ground plates should be located in areas where they can be easily inspected and tested. Fourthly, the grounding electrode system should be installed in accordance with all applicable codes and regulations. The NEC provides detailed requirements for grounding electrical systems, and these requirements must be followed to ensure safety and compliance. In summary, grounding a 400 amp service with a double meter requires careful attention to detail and a thorough understanding of the NEC requirements. By following these steps and considerations, a safe and effective grounding system can be established, protecting people and property from electrical hazards. Grounding is an essential aspect of electrical safety and should never be overlooked. In the context of your question about a 400 amp service with a double meter can and 2 main disconnects, establishing a proper grounding system is paramount. To be precise, the phrase creating your ground at the first means of disconnect refers to establishing the grounding electrode system at the location where the service enters the building. This is typically where the main disconnects are located. This location is crucial because it serves as the reference point for all grounding and bonding within the electrical system. The grounding electrode system typically consists of one or more grounding electrodes, which can include ground rods, ground plates, metal underground water pipes, or concrete encased electrodes, often referred to as UFA ground. The selection of the appropriate grounding electrode depends on several factors, including local soil conditions, the availability of a suitable water pipe, and the requirements of the local electrical code. Once the grounding electrode system is established, it must be connected to the neutral bus at the first means of disconnect using a grounding electrode conductor. This conductor must be sized appropriately based on the size of the service entrance conductors, as specified in NEC Table 250.66. The purpose of this connection is to provide a low impedance path for fault currents to return to the source, which facilitates the operation of overcurrent protective devices such as circuit breakers or fuses. When you mention getting your ground from your main to your panel inside the house, you are referring to the connection between the grounding electrode system at the service entrance and the equipment grounding conductors that run with the branch circuits inside the house. It is essential to understand that the equipment grounding conductors are separate from the neutral conductor and are intended to provide a path for fault currents to return to the source without energizing non-current carrying metal parts of equipment. The question arises whether to run the equipment grounding conductor alongside the service entrance cable, obtain it from the cold water ground, or use either option. The correct approach is to run a separate equipment grounding conductor with each branch circuit. This conductor should originate at the main panel and extend to each outlet and equipment location. It should be connected to the grounding terminals of receptacles, switches, and other electrical devices. It is not permissible to use the cold water pipe as the primary equipment grounding conductor for branch circuits. While the cold water pipe can be used as a grounding electrode, it is not intended to serve as the sole path for fault currents from branch circuits. The reason for this is that the cold water pipe may not provide a sufficiently low impedance path for fault currents, and it may be subject to corrosion or other damage that could compromise its effectiveness. Furthermore, relying on the cold water pipe as the primary equipment grounding conductor could create a shock hazard if the pipe becomes disconnected or if there is a break in the metallic continuity of the piping system. Therefore, it is essential to run a separate equipment grounding conductor with each branch circuit to ensure a safe and reliable grounding system. In summary, to properly ground a 400 amp service with a double meter can and 2 main disconnects, you should firstly establish a grounding electrode system at the first means of disconnect. Secondly, connect the grounding electrode system to the neutral bus at the first means of disconnect using a grounding electrode conductor size according to NEC Table 250.66. Thirdly, run a separate equipment grounding conductor with each branch circuit from the main panel to each outlet and equipment location. Fourthly, bond the cold water pipe to the grounding electrode system, but do not use it as the primary equipment grounding conductor for branch circuits. By following these steps, you can ensure that the electrical system is properly grounded and that people and property are protected from electrical hazards. Additional clarifications. Firstly, the size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the service entrance conductors. For example, if the service entrance conductors are 500 kc male copper, the grounding electrode conductor would need to be at least number 1/0 American wire gauge copper. Secondly, the equipment grounding conductors for branch circuits are sized according to NEC Table 250.122, which is based on the rating of the overcurrent protective device protecting the circuit. For example, if a 20 amp circuit breaker protects a circuit, the equipment grounding conductor would need to be at least number 12 American wire gauge copper. Thirdly, all connections in the grounding system must be made with approved connectors and fittings. These connectors should be listed for grounding purposes and should be installed according to the manufacturer's instructions. Fourthly, the grounding system should be inspected and tested after installation to verify that it is functioning properly. This can be done using a ground resistance tester to measure the impedance of the grounding system. Fifthly, any changes or modifications to the grounding system should be made by a qualified electrician who is familiar with the NEC requirements. This ensures that the changes are made safely and in compliance with the code. In conclusion, grounding a 400 amp service with a double meter requires a thorough understanding of the NEC requirements and careful attention to detail. By following the steps outlined above and consulting with a qualified electrician, you can ensure that the electrical system is properly grounded and that people and property are protected from electrical hazards.